Welcome everyone to the second seminar on statistical mechanics. Today we're going to be talking about entropy in the Boltzmann distribution. So basically our goal is to understand entropy, why it's defined the way that it is, and why we might want to maximize entropy as a thing, and why that's sort of justified or whatever. And then that's heading towards the Boltzmann distribution, which is a distribution that maximizes entropy. We'll start out with a bit of history, because I think it's sort of useful for understanding how different sort of people, so like your physicists and your information theorists, talk about entropy. I guess I'm going to say the history of entropy starts in 1872, although that's not quite true, with Boltzmann's what is now called Boltzmann's H theorem. And this is the sort of first modern expression of entropy. You can check the notes for the paper and a translation of the paper, and it's more or less in there as we might use it today. And in this paper, it was shown that the quantity that we now call entropy can only increase as a thermodynamic system evolves over time. So this showed that some processes in thermodynamics are irreversible, albeit this was shown under assumptions which were considered fairly controversial at the time. Then later, in 1948, we had Claude Shannon brought entropy to the world of information theory. So in this work, entropy is taken to be a measurement of uncertainty inherent to a probability distribution. So if we have a random variable on a probability space, so we'll call RV the random variable X, taking real values, we want to be able to quantify how uncertain we are about X of omega if we don't know the outcome omega. Now this, I'll sort of elaborate a bit on this as we kind of get more into the talk, but this is more or less equivalent, or this is equivalent in some ways to the information inherent in a random variable as well. So Shannon gives an axiomatic description of such a measurement, and then from this axiomatic description derives a essentially unique, so unique up to a change of units, measurement or definition of this measurement in the case that X is a discrete random variable, so one taking finitely many values. And then identifies in this paper, which is cited in the notes, that this is formally identical to the expression of entropy in statistical mechanics. By Shannon's time, this concept of entropy in physics had become widely accepted. And then, I guess to bring it all together, in 1957, we had two papers by James, and this argued that physics entropy is the same as information. It's the same as information entropy. This is less of a mathematical, not an entirely mathematical argument, I would say. It's more of a sort of philosophical or an argument about the point of view you should take on on entropy and statistical mechanics. So readers of this paper, which is cited again in the notes, are invited to consider statistical mechanics as a form of statistical inference. And in the point of view of Jaynes, entropy, or more precisely, entropy maximization, plays the role of model selection. And then they go on to argue that choosing the distribution on phase space, which maximizes the amount of entropy in the system, amounts to choosing the distribution which is, to quote from the paper, maximally non-committal with regard to missing information. I recommend reading that first paper of Jaynes, which is cited. I think it's it's very clearly explained what's going on. Cool. Okay. If there's no questions, we'll now move on to define or to derive the axioms for this measurement of uncertainty along the lines of what Shannon was doing. But before I do this, what I want to talk about is uncertainty versus information. I made this comment that in some sense uncertainty in a random variable is the same thing as its sort of inherent information. So let x be a random variable, and suppose we're highly uncertain about, let's say this is discrete, and suppose we're highly uncertain about the values about this random variable, right? So a way to formalize this is to say, or to express this in mathematical language. So we might say we're uncertain about x by definition if and only if it takes many different values with similar probabilities. So in other words, for any value in its support. So the set of values, the set of real numbers which it takes with positive probability, that the probability that x is equal to that value is reasonably small. Now, what this exactly means is that that the region, so this is just sort of translating the previous sentence, that this region here, so the subset of our outcome space in our probability space, which map to x, is small as measured by P, right? This is just translating the definitions. So in other words, for a random variable that we have a high amount of uncertainty in, knowing that x is equal to some value tells us lots about where we appear in omega, right? Tells us lots about where we are in omega, right? So here, I guess I should have said here we have a probability space, omega, which we're sort of working under. Okay, any questions about that before we move on? Great. Is there a message in the chat? Or...
No. I'll let you know.
Okay, cool. All right, on to the next board. So now we're going to consider some axioms for this measurement of uncertainty. So we'll stick with our random variable x, again assumed to be discrete, and we'll let h of x, suppose we've come up with this measurement, and we'll let h of x denote the measurement of uncertainty. Okay, so one thing that we might be, well, so if a random variable x takes many different values with similar probabilities, then that random variable has more uncertainty compared to a random variable which takes fewer values, also with similar probabilities. So if x takes n values, each with probability 1 on n, say, and y takes m values with probability 1 on m, if m is less than n, then we want that the uncertainty in y should be less than the uncertainty in x. Okay, and okay, so this is just sort of expressing our, what we kind of want to get out of our uncertainty. The other thing that we kind of want is we don't want to be able to change the uncertainty by encoding random variables in different ways. So we don't want to change uncertainty by encoding differently. So let's talk about this using an example before we state the axiom properly. Hey. Suppose x takes values 1, 2, 3, and 4, each with probability 1/4. Right. So if we remember, I guess maybe high school probability, you could draw this using a tree diagram. X equals 2, x equals 3, x equals 4. Each of these is followed with probability 1/4. Well, another way of encoding this is as two different random variables, right? So we could have, first of all, a random variable y, which takes value, so y takes, let me put this in a slightly better spot. So y takes value 0 when x takes values 1 and 2, right? And y takes value 1 when x takes values 3 and 4. And then we have another random variable which is conditionally dependent on y. So when y takes value 0, then z takes value 0 when x takes value 1, and z takes value 1 when x takes value 2. And likewise for when y is equal to 1, that. And then I'll just finish off this diagram like so. So we'll put our representation of our outcome space over here. And then we can think about where we're ending up in this outcome space. Right. So this region here corresponds to either x being equal to 1 or equivalently y being equal to 0, and or perhaps more correctly I should write the vector y z being equal to 0, 0, and this region, I won't fill them all in, but so this region here is x being equal to 3 and y z being equal to 1, 0. Okay, and basically we don't want this to we want the random variable x to have the same amount of uncertainty as the random variables y and z, right? Because fundamentally it's not telling us, changing this encoding isn't telling us anything different about the outcome space of our probability distribution. So we'll just, because I've run out of space there, we'll just jump quickly onto the next board. So what the expression that we're sort of wanting to write down is that the uncertainty in x, well, that's the same as the uncertainty in y, plus the probability that y is 0 what am I writing? So the probability that y is 0, weighting the uncertainty of the conditional distribution of z when y is 0, plus the probability that y is 1, weighting the probability, weighting the uncertainty in z when y is 1, right? Here, this is just the uncertainty in conditional distribution. Okay. Any questions about that?
Can I ask a question, Rohan?
Yeah, for sure.
So, is there a formal definition for encoding a random variable?
Yeah, not as I've been sort of using it, I think. I think though, what Ben, would you mind just going back to that previous board? What I'm trying to get at with this picture, and what I've been kind of wondering about as I've been writing this talk, is really it seems like for a random variable, say let's not reuse a letter. I'll write this in a different color. For a random variable, say W, we can talk about the sigma algebra that's been generated by W, right? So looking at the set of all, yeah. If are you familiar with that? Yeah. And we kind of, what this is kind of getting at least it seems to me what this axiom is getting at, is that if two random variables, or in this case a random vector, as some people say, and a random variable generate the same sigma algebra, then they should have the same uncertainty. Now, I haven't proved that this is true of entropy, but I kind of think that you probably could make a definition of entropy in terms of sub-sigma algebras rather than in terms of random variables. So that's the way I'm thinking about it. It turns out we don't need to make such a large assumption. We only need to make a kind of not quite what I've written up here on the third board, but only a slightly sort of like an iterated version of this where we might encode this as, n random variables rather than just a finite number. Cool, thanks. Any other questions? Cool. Cool. All right. Now, yeah, so it turns out that all we need in order to uniquely specify entropy up to a change of units are these two assumptions along with a continuity assumption. So that's kind of cool. Now, before we talk about this proof, I'm going to just state a lemma. Depending on how we're going for time, I'll prove it at the end, or it's in the notes. I guess I followed Shannon's proof for this, so I guess I'll credit Shannon, although it seems likely this was probably known before. So we'll let A be a function from the natural numbers, not including 0, to the real numbers. What am I trying to write? B, monotonic increasing function, satisfying the following condition. For all our natural numbers, then it's necessarily the case that A of n is equal to k times log n for all n, where k is some fixed positive constant. Okay, proof. We'll either get to that if we have time, or you can read the notes or Shannon's proof, or have a go yourself. Cool. I'm going to now introduce some notation, and then we'll move on to the statement of the theorem. So we'll let big capital delta to the n. This is going to be the set of all probability distributions on n symbols. Sort of skipping out on the ones which are not actually on n symbols. So we don't want any of these probabilities to be 0.
Can there be 1?
Well, no, if none are 0, because we have this condition at
true.
the end. Yeah. I guess for n equals 1, they can the 1 can be 1, and in fact has to be.
Yeah.
Okay. So this is the set of all probability distributions. With support of size n, right? So we're just identifying these vectors with their probability distributions, and then we're going to think about all of these at the same time. So we're going to take the union of all of these, and this is the set of probability distributions with finite support. And now we're ready to go ahead and state our theorem. So we'll move over to the second group of boards here. Cool. Okay, so this is the theorem due to Shannon. The full citation is in the notes. So we'll let H be a function from the set of finitely supported probability distributions, which satisfies the following assumptions. So 1, H is continuous. 2, the function which we define like so is monotone increasing in n. Okay, and now, so that was our first sort of derived assumption where, if we take more different values, then we should be more uncertain about our random variable. The next one is our sort of how we're going to formally express our kind of re-encoding idea. So if we have a probability distribution P1 through Pn, we can consider the distribution obtained by grouping the first n1 events together. So we can group the first n1 events, right? The next n2 events, and so on. Where we have these numbers add up to the total number of events we have, right? So we have the n1 plus n2 plus n3 and so on up to, I guess, nm is equal to this, right? So, okay, yep, we're going to do that. And then we can think of the distribution obtained in this way, right? So we can think of, we have a distribution which I'll denote Q1 and Qm, where Q1 is just P1 plus P2 up to Pn1, right? And Q2, well, that's the probability of the next n2 events. So it's Pn1 plus 1 plus all the way up to Pn1 plus n2. And so on. The notation's getting kind of challenging at the moment. And then we're going to assume that that H has the following relationship between these two probability distributions. So we want, I'll just write this for the vector P, that this amount of uncertainty has to be equal to the amount of uncertainty in Q plus Q1 times P1 on Q1, Pn1 on Q1, right? So this is like a conditional distribution. Of the events in the first N1 events conditioned on the fact that at least one of them has happened, and then so on, right? So this is getting increasingly difficult to sort of express in notation. But we'll do the same thing for the next N2 events as well. Cool. And ... right? Up to the amount of, up to the events contained within, you know, that are accounted for in the QM probability. Okay. So these are our assumptions. Is that somewhat clear? The last one's kind of complex, but it's really just an iterated version of the example we showed before. We haven't stated anything yet. Okay, cool. On to the next board. So here's the statement of the theorem. Then H is of the form that H of P1 through Pn, that this thing is of this form. For some fixed positive number. Cool. All right, so let's prove this. Okay, so suppose H satisfies conditions 1 to 3. Since H is continuous, it suffices to show, let's give this equation a name. Oh, okay, maybe not one. A, to show that A holds when P1 through Pn are rational. So that's the only point we use our assumption number 1. Okay, so we'll let n1 through nn be such that p1 is equal to n1 on the sum of all of them. Well, I guess I'll write pi. Here we go. Oh, maybe not mix indices like that. So we have that pj is equal to nj on the sum from n1 all the way up to nj. Okay, so cool. I'm gonna make a claim and then I'm gonna justify it. So claim by our assumption number 3, we have that the H of P1 through Pn is equal to minus K. Oh no, sorry, I'm restating the theorem. That this is of the form. Oh, sorry, this is not an expression of this. It is an equation involving this. That it is can be written like so. that thing is equal to A of the sum of all of them. Right. Okay, so let's justify this claim. So it follows from assumption number 3. To justify this, maybe I'll just go to another board. So proof of claim. Consider the distribution. Which distribution are we considering? Distribution on this many choices, where each is equally likely. Okay. The entropy, I guess I haven't called it that, but H of this distribution is, I guess I'll just write is the entropy, i.e. H of this is by definition this thing. Great. Now, our original distribution can be obtained from this distribution by grouping the first n1 events together, the next n2 events together, the next n3 events together, and so on, right? Using 3, right? So P1, Pn is obtained by grouping the first n1 events, the next n2 events, and so on. Okay, and then if we apply assumption if we apply assumption 3, gives the claim. Okay. So, given this claim, it suffices to find A of n for all n. Oh, good. Okay, let n and m be integers, and consider the uniform distribution on n times m choices. If we apply, I guess by grouping this into n events of 1 on m, so each having 1 on m probability, we find the expression n times m, A of n times m is equal to A of n plus A of m. And this is exactly the statement we had in the lemma before. So by the lemma, we have that A of n is equal to k times log n for some. Okay, and now it just remains to sort of plug this thing back into our original thing. So I'll just make a note. So we'll call the statement in that claim before, we'll call that B, get that equation B. And then, so by plugging this into equation B, we end up at the following. So rearranging for H, this thing is going to be K times log of this sum minus K times the sum here. Okay. Now, what can we do? We can sort of artificially start summing over these probabilities here. Right. And then bringing everything together and using our log laws, we end up at something that looks like this. Cool. And then remembering how we defined the PI and moving a negative sign outside, we get this. Oops, sorry, this should be a P. And this is also PI. Cool. And this basically completes the proof. It's fairly straightforward to check that this log expression here actually does indeed then satisfy the assumptions that we went into this with. So this completes the proof of Shannon's theorem. Cool. Any questions about that? How are we doing for time?
It's like 40 minutes in.
Okay, cool.
So 110.
Cool. Okay. If there's no questions, let's go back and take a look at the first group of boards once again. We can probably get rid of the history. Okay. I'll wait for everyone to walk over.
Walk so slowly.
Okay. So now we're going to talk about entropy maximization. Okay, so suppose we have a set of candidate distributions to model some system. And all of these candidate distributions are compatible with what we know about the system. So we've made some observations of the system. You could think about these observations as being knowing the expectations of certain functions of this system. And that's good. It's sort of narrowed down our candidate distribution somewhat, but we still have a whole bunch of different distributions which are compatible with our observations. So it's argued in Gaines' sort of very famous paper that since entropy is a measurement of uncertainty, so uncertainty, then we should choose one which maximizes entropy. Okay, and then James argues that if we choose a distribution which does not maximize entropy, then this amounts to introducing additional assumptions which are not based on our knowledge of the system, right? So just arbitrarily introducing more assumptions. I really recommend reading the paper. I'm not going to sort of go through, just repeat what's going on there. I think it's very well written. I probably couldn't do it justice, but yeah, I think it's going through those arguments are sort of very interesting. In this part of the talk, we're going to talk about finding the maximal entropy distribution in the case that we know the expected value of some function, and the case that we know all our candidate distributions have the same finite support. Okay, so we're going to let or rather we're going to consider.
Just before you start,
Oh, yeah.
the assumption of sort of knowing the expectation value of say the energy rather than the exact value of the energy, that kind of like from a thermodynamics perspective puts us in the like canonical ensemble rather than microcanonical, right?
Yeah, that's right. I'm probably not going to go fully into the derivation of the canonical. Well, no, I'm not going to go into the derivation of the canonical ensemble in this talk, although it pretty much gets there. There's just a bit more work to do. But yeah, that's correct. Although, yeah, that's correct. Cool. Any other questions? Great. So we're going to consider now these finitely supported on a set of n distributions to be distributions on a particular set X. So meaning we identify P, so some probability distribution P with a random variable XP, such that it takes value Xi with probability Pi. Cool. And I guess we can just launch straight into this theorem, which is basically deriving the Boltzmann distribution in the discrete case or in the finitely supported case. So theorem. I don't know where to credit this theorem, by the way. So if there's like some canonical reference, it'd be good to know. For some function from our set X to, well, we'll say reals, not identically 0. And a value f. We consider the distributions such that the expected value of f with respect to this distribution is capital F. Okay, to spell this out, because we'll need to look at this formula later, that means precisely this. Cool. And we're going to label this equation C of the P satisfying C. The one with maximal entropy is given as follows. So for each I through from 1 to n, it's given as follows. Whoops, that's too many equal signs. As this, where Z is this thing. Okay, cool. For some value, for some real number beta. All right, let's move on to the proof, onto the next board. Okay, so to spell things out, we want to maximize this thing. Subject to two constraints. that the sum, well, that this thing is actually a probability distribution. That's a terrible summation sign, but that's okay. And that, of course, it has the expectation that we want it to have. Cool. Now, since f is not identically 0, which was one of our assumptions, we use Lagrange multipliers to do this. So we define the following function. So we'll let alpha and beta be real valued variables, and we'll think about this function. So yeah, I won't go in this talk into the method of Lagrange multipliers. I possibly might write some notes on it to supplement this talk if I have time. Okay. Now we can take the derivative with respect to the pi. Okay, and set it to 0. Now, solving for pi will give that pi is equal to e to the minus beta f of xi, e to the 1 plus alpha. Okay, and we're going to set z to be e to the 1 plus alpha. And then using, I guess I'll label this constraint D up here. So using, maybe I've reused this letter. So using D, we have that 1 is equal to 1 on Z times the sum of the pi, which we now know is this. Which gives, where should I write this? Which gives Z, of course, to be what we claimed, which completes the proof, right? We could then go on, so I said for some beta, you would then, to sort of finish this off, use your additional constraint. So that's where this constraint comes in here, say E. You could then go and use that to solve for beta. And that's kind of where, in physics, we have this interpretation of beta being the inverse temperature. Here, this would be, we would know the expected energy value of our system. And then going ahead, and if we know that, the expected energy of our system is such and such a value, then beta would wash out to be 1 on the temperature, possibly times some constants, if you care about units, to be the answer there. Cool. What's the time?
1:20.
Cool. This goes for an hour. Okay, so I got maybe 9 more minutes. Were there any questions about this proof? Great. Let's go to the next board again. Cool. Okay, so I'll just mention that, that the theorem can be extended to the case of multiple constraints. So if you've made multiple observations of the expectations of a bunch of different functions, then you can do the same thing in using a very similar method. The statement of the theorem is in the notes. It's what you'd expect. But nothing too much else to say on that. And then now I want to just briefly talk about continuous distributions, mostly to say that I'm still kind of confused about them. Okay, so up until now, we've been only working with finitely supported distributions. And what we notice that for, say, these finitely supported distributions, that the entropy of a finitely supported random variable x, well, that's just the same thing as the log of this thing here, where p is the, I guess, probability mass function. It's usually called for a discrete random variable. Now, this suggests the following definition. So let y be continuous, so a continuous random variable. Then we could define this is called the differential entropy of y to be just, well, the expectation of the log of is q of y. Which is this thing here. It's meant to be a sort of curly y, q of y log q of y. Okay, so Shannon wrote this down in the same paper, but unlike the discrete case, there was no justification for defining entropy in this way, so it doesn't have a nice theorem to go along with it like we had for how we derived our expression for entropy earlier. And from reading around, it seems like this is, some people say this is not the right way of defining entropy for certain reasons that I'm not fully across yet. An alternative, which will be familiar to a lot of people here, is the relative entropy relative to some fixed distribution phi. So relative to a fixed distribution, say phi. The relative entropy is also called the KL divergence, and we'll look at the divergence of y with respect to phi, and that washes out like so, where I guess curly y is the space y takes values in. Okay, and then from relative entropy, one can define the Boltzmann distribution in a similar way. So you could define this to be like so, where z is yeah, and so as I understand this, if going from here to here is sort of using, I guess it's called calculus of variations, which seems, from what I've read, seems legit, although I haven't looked at it in too much detail. I guess the thing I'm still confused is as to the reason for making these distributions, or sorry, these definitions, or maybe this definition, and then hence why are we justified in looking for a distribution which maximizes this? So if anyone's got anything interesting to say about that, or somewhere to read about that, then let me know. I might sort of update this later with another talk or with another note or something. I think that's just about. Oh yeah.
Oh, sorry. I was just gonna answer your your prompt there, because Jaynes sort of argues that the proper continuous analog of like what you kind of hope for from a continuous definition of entropy is that it's effectively like the limit as you take n to be infinity. Like you have some continuum that you're discretizing, and then you look as your discretization gets finer and finer. And actually the differential entropy is not that. It's instead the limiting density of discrete points, LDDP, which is the KL divergence from a uniform distribution to your distribution, which plus a log n term. It's on the Wikipedia page for that, and the Kale divergence, I know only vaguely, but you can justify it via like it's essentially like if you have a prior and a posterior, then the Kale divergence is the number of bits that you need to update from your prior to your posterior, but how you formalize that I can't remember.
Yeah, okay. I guess it's that last part's the thing I'm really interested in is like, you know, is there some sort of analog that shows if you assume entropy measures, you know, uncertainty or information or something like that sort of demonstrates that your KL divergence or your limiting density of discrete points entropy or whatever you choose, that it actually does seem to represent that in some sort of unique fashion. It's sort of similar to how we did for the discrete case. So if you remember where you read about that, then I'd be very interested to see that.
Yeah,
but yeah, thank you.
Look that up.
Thank you. Any other comments or questions?
So what happened to the negative side in the expectation? Is it a typo?
Yes, thank you. Whoops.
Oh.
Yeah, negative here, negative here. Negative here.
In the first line, the definition has a negative one. In the first line.
Where we?
The h of x at the top.
Oh, yeah. Cool. Yeah. Cool. Any other comments, questions? Okay, cool. If there's no other comments or questions, we might leave it here. If you want to see a proof of that lemma involving the logs, check the notes. I'll just mention I've written up what I'm thinking of doing going forward in future seminars. So I want to get more. So I think these last two seminars, like you just sort of have to cover this kind of stuff if you're looking at statistical mechanics. At least that's sort of the impression I got. But now I want to start looking more at dissipative systems. So statistical mechanical systems which dissipate energy over time. Now, looking into this, it seems like to do this sort of well and rigorously, we need to understand a fair amount about stochastic processes and stochastic differential equations. So we'll probably have one or more talks on that. And my goal is to understand enough about those to understand chapter 7 of a book called A Modern Course in Statistical Physics, which covers Langevin dynamics, the Fokker-Planck equation, and Brownian motion from a physicist's perspective. So looking at, you know, the grain of pollen in the liquid, trying to understand the physics of that motion. And I think once we've done that, we're in a really good position to start looking at some of the deep learning papers or learning papers that I want to look at. So there's one in particular called Statistical Mechanics of Learning from Examples. This is a paper that uses Langevin dynamics as a model for neural network training, which is probably not quite correct, but they still do a lot of cool stuff. They apply a lot of cool statistical mechanical techniques at various points to derive certain things, so I'd like to really get stuck into that and understand that one. Cool. Let's leave it here. And yeah, thanks everyone for coming.
Thank you.
Thank you.
Oh, whoa. Is that
your notes?
this is what's written on the sky?
It's from the Euclid seminar. So whatever you wrote on the first board over there, Billy made it so that it gets projected onto the sky. So if you
That's kind of dystopian.
it's Euclid. How can you feel it's not that ominous?
Euclid comes back and terrorizes everyone.